Today, we are undertaking a monumental journey. I mean, we're not just exploring a book, we are exploring an entire worldview.
We are strapping ourselves into the ship of the imagination to unpack one of the most seminal works of modern science communication, Cosmos by Carl Sagan.
Absolutely. This book and the series that went with it, it really did change how a whole generation looked at science.
It made the complex accessible, the vast tangible, and frankly, just made the facts sound beautiful. It's like a complete framework for thinking about our existence.
That's it, exactly. Our mission here is to unpack the core ideas of this masterpiece. Sagan connects all the dots between the history of science, the origin of life, and just the mind-bending scale of it all.
And the central concept for this entire deep dive is right there in the title, Cosmos. It's a Greek word, and it means more than just universe.
Yeah, it means the order of things, the deep interconnectedness of everything, which is the exact opposite of chaos.
So we're going to follow his argument chapter by chapter and see how he builds this incredible ordered world for us.
Let's start with chapter 1, the shores of the cosmic ocean.
Sagan always starts with humanity, doesn't he? He shows us the roots of our understanding.
Right. He begins not with telescopes or anything, but with a simple attempt by early people to explain suffering. He uses this fascinating Assyrian incantation against a toothache from around 1000 BC.
It's an incredibly powerful way to start. This Assyrian wisdom ties a really common, painful, mundane thing, a toothache, to the grandest cosmic events.
The incantation basically says the god Anu created the heavens created the earth created rivers, and so on, and you follow this chain of creation all the way down to the worm that causes the toothache.
Which just shows how small and tidy their cosmology was. Humans were at the very center of the story, and the universe was small enough that, a god's action could cause a dental problem.
Exactly. And then right after establishing that, Sagan just shatters that tidy little world. He throws us into the true, overwhelming scale of the cosmos.
Yeah, that mental voyage outward. It's designed to completely shift your perspective.
We start 8 billion light years away. You're looking at galaxies as these faint, wispy tendrils of light, all huddling together in these massive clusters.
And the light you're seeing left those structures before the Earth even formed.
Then as you get closer to our own home, the Milky Way, the numbers just become paralyzing.
It's a vast collection of something like 400 billion stars, a giant spiral that takes 250 million years just to make one rotation.
And within all that, we find our sun, a completely unremarkable, solitary yellow dwarf star.
Located way out on the remote outskirts of a spiral arm. We are emphatically not at the center of anything.
Not even close. And then you zoom past all this incredible diversity supernovae, black holes, blue giants, red dwarfs, down to our solar system.
You pass through the Oort cloud, the swarm of comets, past Pluto and the gas giants, and then you finally return to Earth.
But the view is fundamentally changed.
It's this tiny, fragile, blue-white world. And it's so poignant because, as far as we know, in all that vastness you just traveled through, this is the only place where matter has become alive and aware.
That shift in scale is everything. But then Sagan shows how simple ingenuity first cracked the code, which brings us to Eratosthenes of Alexandria.
The director of the Great Library. A polymath who his rivals called Beta, probably out of jealousy.
And he achieved something monumental with just astonishingly simple tools.
His genius moment came from reading a papyrus scroll, right?
That's right. It mentioned that on the summer solstice, a stick placed in a town called Syene, far to the south, cast no shadow at noon.
But Eratosthenes knew that a stick in his own city, Alexandria, which was far to the north, cast a really substantial shadow at that exact same time.
And that's the aha moment.
That difference must mean the Earth is curved. If it were flat, both sticks would cast the same shadow or no shadow.
Exactly. The parallel rays from the distant sun hitting a curved surface. So he measured the angle of the shadow in Alexandria, which was about 7 degrees.
And 7 degrees is, what, about 150th of a full 360-degree circle?
Precisely. So the next step was the calculation. He needed to know the distance between the two cities.
Which he got by hiring a guy to literally pace out the 800 kilometers between them.
I mean, can you imagine? That alone is an incredible feat of organization. But once he had that number, the math was just beautiful.
So if 800 kilometers is 150th of the planet's circumference, he just multiplied 800 by 50.
And got 40,000 kilometers.
That's your correct answer. Within a few percent of today's measurements. Over 2,000 years ago, with sticks, eyes, feet, and brains. It's just incredible.
It really is. And you have to pause and think about the glory of Alexandria itself. The library wasn't just a place for books.
No, it was the first real research institute dedicated to establishing order, to establishing cosmos.
You had Hipparchus cataloging stars there, Euclid creating geometry, Herophilus figuring out the brain as the seat of intelligence.
And tragically, Hypatia, the last great scholar, who was murdered as that light was going out.
The tragedy is just so profound because it's about knowledge that was deliberately destroyed. And the most bitter irony is that an astronomer there, Aristarchus, had already figured out that the Earth orbits the sun.
And we lost that knowledge for 2,000 years. It was suppressed because it was seen as dangerous.
Alexandria was eventually obliterated by oppression and a fear of learning. It's this terrifying lesson that intellectual glory isn't enough to save a society if that society won't protect rational thought.
Okay, so from the scale of space, we move into chapter 2. One voice in the cosmic fugue. This one is about the scale of time and life itself.
Right. And it starts with this realization that all life on Earth, from a microbe to a sequoia tree to us, shares a common organic chemistry and evolutionary heritage.
We're just a single data point, one lonely theme in what Sagan calls the cosmic fugue. We have no idea what other notes life could play if it started somewhere else.
That unity is what points to the fact of evolution. The mechanism, of course, being natural selection discovered by Darwin and Wallace.
Nature is prolific, mutations provide the variety, and the environment does the selecting.
And to make this really visceral, Sagan tells this great story that demonstrates selection, but it's a kind of artificial selection. The story of the Hike crab in Japan.
Oh, this is a great one. The shell of this crab has an uncanny resemblance to the face of a samurai warrior.
Exactly. And that pattern became culturally significant because of a famous naval battle in the 12th century where the Hike clan ground.
So Japanese fishermen, being superstitious, would catch these crabs, see the face of a dead warrior, and throw them back into the sea out of respect.
So the fishermen themselves became the selecting agent. The crabs whose shells looked most like a samurai face were the ones that got to survive and breed.
Over centuries, the resemblance just got more and more pronounced. It's a perfect example of how a selective pressure can guide genetic change.
It really is. And it helps you grasp the timescale because the real challenge is comprehending the eons. We live for such a short time.
Right. The secrets of evolution are death and time, vast amounts of time.
Which brings us to the chemistry, the origin of life. Sagan argues life arose really quickly after the Earth formed, maybe 4 billion years ago.
And he details those famous lab experiments that simulate the early Earth.
Yeah, they take these simple hydrogen-rich gases, methane, ammonia, water vapor, and they zap them with energy to simulate lightning or UV light.
And what happens?
The vessel gets coated in this thick brown tar, and when they analyze that tar, it's full of complex organic molecules.
The building blocks of life. Amino acids, the components of proteins, and nucleic acids.
The point being that the notes of life are easy to make. The universe seems to tend toward this kind of complexity.
And those notes assemble themselves into the instructions for life, DNA, and RNA. Our DNA has something like 5 billion bits of information.
It would fill 1,000 volumes if you wrote it all out. But the truly amazing part is the molecular unity.
A tree and a person share the exact same genetic code book for translating that information.
Which strongly suggests we all come from a single common ancestor, one origin of life on this planet.
But then, of course, Sagan turns the question outward. What if the cosmic fugue plays elsewhere? What would life look like on a gas giant like Jupiter?
He and his colleague E.E. Salpeter did calculations on this. They imagined life forms that could survive in the upper cloud layers.
They came up with sinkers and floaters.
Right. The sinkers are tiny organisms that reproduce really fast before getting carried down into the hot layers and fried.
But the floaters are the amazing ones. These vast, city-sized organisms that are basically living hydrogen balloons.
Floating in the atmosphere, maybe making their own food from sunlight. It's wonderful speculative.
A great reminder that our imagination is the only limit when we think about what life could be out there.
So from biology, we move into Chapter 3, the harmony of the worlds, and the mechanics of the heavens with Kepler and Newton.
Kepler's story is all about this profound, almost religious drive. He was convinced that mathematical harmonies governed everything.
His first big project, the cosmic mystery, was based entirely on a delusion.
He thought he could fit the orbits of the 6 known planets into the 5 platonic solids, nested one inside the other.
It's a beautiful idea, aesthetically. But it was completely wrong. The data just didn't fit.
His real triumph came from observation. He inherited Tycho Brahe's incredibly precise data.
And that data forced him to abandon the ancient belief that orbits must be perfect circles, which was a huge psychological hurdle for everyone at the time.
He eventually realized that, the Earth itself is imperfect. It's full of war and famine, so why should its orbit be perfect?
So he tried different curves and finally landed on the ellipse, a formula codified centuries earlier in Alexandria.
And it fit Tycho's observations of Mars perfectly.
It was a total victory for observation over his own dearest illusions. And that gave us Kepler's first law. Planets move in ellipses, not circles.
But his personal story is just as compelling. He was exiled for his beliefs, and then he had to defend his own mother against accusations of witchcraft.
Can you imagine? It's the height of the 30 Years' War, paranoia is everywhere, and he's using rigorous scientific reasoning to save his mother from being burned at the stake.
It perfectly captures that transition from the old world of superstition to the new world of reason.
And that paved the way for Isaac Newton, who was born the same year Galileo died.
Newton was famously impatient with mysticism. But funnily enough, he actually got into math because he bought an astrology book and couldn't understand the calculations.
Right, he had to teach himself trigonometry just to figure it out. And that led to his miracle year in 1666, during the plague.
Where he basically invented calculus, figured out the nature of light, and founded the theory of universal gravitation.
He was the first to truly unify the heavens and the earth. He realized the force pulling an apple to the ground was the exact same force pulling the moon in its orbit.
Gravity.
And he codified it in the inverse square law. That means gravity gets weaker as the square of the distance.
So if you're twice as far away, the force is only 1/4 as strong.
Exactly. And that law applies everywhere. It was the mathematical harmony Kepler had been looking for all along.
Okay, so that brings us to chapter 4, Heaven and Hell, which moves from harmony to cosmic violence. It starts with the Tunguska event in Siberia in 1908.
The eyewitness accounts are just chilling. Tents blown away, the sky on fire, a wind like a cannon blast. It leveled 2,000 square kilometers of forest.
But the key clue was that there was no impact crater.
Right, which means it wasn't a solid object that hit the ground. The best theory is that it was a fragment of a comet, maybe 100 meters across, that exploded high in the atmosphere.
A 1,000,000-ton icy snowball vaporizing in the air.
Comets used to be terrifying, harbingers of doom. But Newton showed they just follow predictable elliptical orbits.
And we now know there's a huge swarm of them out in the Oort cloud, trillions of these icy nuclei.
And the frequency of these impacts is pretty sobering. Something like Tunguska happens every 1,000 years or so.
And you see the evidence for this all over the moon, which is just covered in craters.
Because the moon has no erosion, no wind, no water. The Earth gets hit just as often, but our planet wipes the evidence away. Meteor crater in Arizona is only about 20,000 years old, which is nothing in geological time.
Then the chapter pivots from that external threat to an internal one, looking at our sister planet, Venus.
For centuries, people imagined it as this lush, swampy, Earth-like world because you couldn't see through the clouds.
But the reality turned out to be a planetary hell.
An atmosphere of 96% carbon dioxide, clouds of sulfuric acid, and a surface temperature hot enough to melt lead.
About 480 degrees Celsius. And it's all because of a runaway greenhouse effect.
This is the terrifying part. Venus is just a little closer to the sun. That extra bit of heat baked carbon dioxide out of the rocks into the atmosphere.
The CO2 acted like a blanket, trapping more heat.
Which baked out more CO2, which trapped more heat, and you get this catastrophic feedback loop until the entire planet's climate goes into thermal runaway.
And the really critical warning for us is that Earth has just as much CO2 as Venus. Ours is just safely locked away in rocks like limestone.
If you moved Earth just a little bit closer to the sun, we could suffer the exact same fate. Venus is a chilling object lesson.
From Venus, we go to Mars in chapter 5, Blues for a Red Planet. This is all about the search for life.
And you have to start with Percival Lowell and his famous canals.
He popularized this idea of a dying Mars, where an ancient civilization built these vast irrigation ditches to bring water from the poles.
And that idea really captured the public imagination in the late 19th century. They were building the Suez and Panama Canals, so it seemed plausible.
But of course, the reality delivered by the Viking probes decades later was no canals, not a single one.
Lowell was just seeing what he wanted to see. As Sagan said, the only intelligence involved was on which side of the telescope.
So the Viking mission mapped the planet and found all these amazing features. Ancient riverbeds, giant volcanoes. But its main goal was to find life.
The landers ran these complex microbiology experiments, feeding nutrients to the soil to see if anything would, metabolize it.
And the results were ambiguous. But the real killer blow to the idea of widespread surface life was something they didn't find.
No organic molecules in the soil.
Right. If there was life, even dead life, you'd expect to find complex, carbon-based molecules. Their absence was a profound negative result.
The conclusion was cautious but clear. There's no evidence for life in the soil where and when they looked.
So the next step is either a sample return mission, which requires stupefyingly reliable containment.
Or, even better, a rover that can travel around, drill under rocks, and explore more interesting places than the flat, boring landing sites they chose for safety.
And the chapter ends on this beautiful irony.
The idea of terraforming Mars, making it habitable for humans, might involve melting the polar caps and digging great canals to transport the water to the equator.
So we might end up building the very civilization that Lowell mistakenly thought was already there.
Let's jump back in time now to Chapter 7, The Backbone of Night, which is about the very birth of scientific thought.
Before science, there was myth. The Kung Bushman called the Milky Way the backbone of night, which is just beautiful.
But those myths all relied on gods and spirits. The real awakening, the birth of science, happened in Ionia, in the Greek colonies, between 600 and 400 BC.
Why there?
It was a crossroads of civilizations, so no single god hypothesis held total sway. And power was held by merchants who valued practical technology, not just priests.
And the great idea that was born there was revolutionary. That the world could be understood through natural laws without gods pulling the strings.
Which led to pioneers like Thales, who predicted an eclipse, and Democritus, who came up with the idea of atoms.
And Anaxagoras, who said the moon shines by reflected light and the sun is just a giant flaming rock.
A very dangerous thing to say back then. He was condemned for it. And that highlights why this Ionian awakening didn't stick.
It was the Pythagorean legacy that ultimately sealed its fate.
Pythagoras himself made huge contributions. He figured out the Earth was a sphere. He even coined the word cosmos.
But he also introduced a fatal flaw. The belief that you could figure out the laws of nature by pure thought alone, without messy experiments.
And that led to a disdain for manual labor, which was reinforced by the slave economy. Experimentation was seen as work for slaves, not for philosophers.
So the hands-on Ionian method was abandoned for 2,000 years. It was a catastrophic detour for human progress.
And that detour finally ends in Chapter 8, Travels in Space and Time, where we get back to the deep questions.
Starting with the idea that looking out into space is looking back in time.
Because of the finite speed of light, light from the Andromeda Galaxy left 2 million years ago. We're seeing it as it was long before humans existed.
And light from distant quasars left 8 or 10 billion years ago, before the Earth even formed.
And this leads directly to Einstein and special relativity,
which completely challenges our common sense notions of time and space. Einstein gave us 2 commandments of nature.
First, the cosmic speed limit. You can't travel at or beyond the speed of light. And second, that the laws of physics are the same for everyone, no matter how they're moving.
And if you accept that, then time and distance become flexible. You get effects like time dilation.
The famous twin paradox. An astronaut twin travels near the speed of light and returns home only a few years older, while their twin on Earth has aged decades.
So traveling fast into space is also traveling fast into the future.
This brings us to the structure of the universe itself, which we know is expanding because of the Doppler effect.
Right, like a car horn changing pitch as it drives by. With light, a source moving away from us is redshifted.
And the stunning fact is that almost all distant galaxies are redshifted. They're all rushing away from us, evidence for the Big Bang.
To help us grasp the shape of it all, Sagan uses the analogy of flatland.
A 2D world curved through a third dimension. So by analogy, our 3D universe could be curved through a fourth dimension, a hypersphere.
Which would be finite, but have no boundary, no center, and no edge.
Exactly. The expansion of that hypersphere is what makes all galaxies seem to be receding from each other from every point of view.
Finally, in this chapter, he talks about finding other planets.
We can't see them directly, but we can infer they're there by detecting the tiny gravitational wobble they cause in their parent star.
And simulations show planetary systems are common. There could be 100 billion of them in our galaxy alone.
So from countless planets, we move to Chapter 9, The Lives of the Stars, the cosmic kitchens where all the matter comes from.
This is where Sagan gives us his most famous analogy, the apple pie.
To make an apple pie, you need atoms. Carbon, oxygen, hydrogen. But except for hydrogen from the Big Bang, All those other elements were cooked inside stars.
If you wish to make an apple pie from scratch, you must first invent the universe.
Stars are fusion factories. In their cores, they fuse hydrogen into helium, then helium into carbon and oxygen, and so on, up to iron for the most massive stars.
Our sun is a second or third generation star. The carbon in our bodies, the iron in our blood, was forged inside a star that lived and died long before we existed. We are literally stardust.
But our sun has its own fate. Billions of years from now, it will swell into a red giant, boiling away Earth's oceans and atmosphere.
It'll shed its outer layers as a beautiful planetary nebula.
And the core will be left behind as a white dwarf, incredibly dense, a ton per teaspoonful, that will slowly cool for trillions of years into a dead black dwarf.
But the deaths of stars are vital for life. The supernova explosion not only creates and scatters the heavy elements,
But the shockwave might have been what triggered the formation of our own solar system.
and maybe most fascinating of all, cosmic rays from those explosions bombard Earth, causing genetic mutations.
Which provides the raw material for natural selection. The death of distant suns drives evolution right here.
So we jump now to the end, to Chapter 12, Encyclopedia Galactica, which ties all this together and asks about our future.
Given the hundreds of billions of stars, it seems statistically probable that millions of worlds are inhabited by advanced intelligence.
Which is the whole rationale for SETI, the search for extraterrestrial intelligence using radio astronomy.
But that leads to the great, chilling question. The Fermi paradox? If they're out there, where are they? The great silence.
Sagan explores the uncomfortable possibilities. Maybe we're the first. Or maybe they're hiding from us.
Or the most chilling one. Maybe technical civilizations inevitably destroy themselves during their technological adolescence.
They invent things like nuclear weapons before they have the wisdom to control them.
And that's the survival justification for SETI. If we get a message, it proves that someone figured it out, that someone survived. That knowledge alone would be profoundly hopeful for us.
Sagan also points out that any interstellar civilization must have first solved population control.
Otherwise, all their resources get swallowed up just maintaining their local population, with nothing left for grand projects like space travel.
This brings us back to the danger we face now. The same rockets we use for exploration are poised to deliver nuclear warheads.
And the scale is just staggering. All the bombs dropped in World War II equal about 2 megatons. A single modern bomb can equal that. Global arsenals hold over 10,000 megatons.
It's 1,000,000 Hiroshima bombs. And Sagan cites this sobering model that suggests if our propensity for war hasn't diminished since 1945, doomsday may be just decades away.
Which is why the lesson of Alexandria is so critical. The library was destroyed not because the scholars were ignorant, but because they failed to engage with their society.
Science remained the exclusive property of a privileged few.
So when the mob came to burn it down, there was no one to stop them. The public had no stake in defending it.
Our path forward has to be rooted in the cosmic perspective. From space, national boundaries vanish. It's hard to maintain fanatical chauvinism when you see the Earth as a fragile blue crescent.
And science is our best tool because it has 2 rules. There are no sacred truths, and anything inconsistent with the facts must be discarded.
We have to see the cosmos as it is, not just as we wish it to be.
I think the power of cosmos is that synthesis. It reminds us over and over that we are children of the sky and the earth, made of stardust.
We're all connected through a common origin, and we possess this incredible intelligence in our cerebral cortex to figure it all out and secure our future.
But the Darwinian lesson is clear. We are a rare and endangered species. The chances of finding other humans elsewhere are basically zero.
Oh, here, only on this small planet.
So every one of us, in the cosmic perspective, is profoundly precious.
Which leads to that final provocative thought that Sagan leaves us with, challenging our immediate priorities.
He asks you to think about the staggering amount of money we waste on conflict, the tens of billions spent every year on military weapon systems.
That money could have funded decades of planetary exploration, decades of SETI research. It could have advanced the very knowledge we need for our long-term survival.
So the choice between self-destruction and a future among the stars really hinges on how we prioritize our limited resources right now. That choice, made today, determines whether we join the wider cosmic fugue or remain just a brief, lonely note.